So last set of reactions we're going to talk about are reduction reactions of benzene. Benzene is extremely hard to reduce all the way to cyclohexane. Remember that if we had something like this, we could just have H2 and like a nickel catalyst, and that would get me to an alkane. Because benzene is so stable, you need to use really harsh conditions. So by that, I mean 150 degrees Celsius. That's really freaking hot. And 1,000 ATMs. So the pressure has to be 1,000 times more than what it is just here right now in this room, right? So really harsh conditions in order to actually reduce those double bonds in a benzene ring to cyclohexane. It also means selectively that if you started out with, right, this was styrene, or any double bond that's outside of that benzene ring, and you use some of those more gentler conditions, you will selectively reduce that. Well, don't want to do that. You will selectively reduce the double bonds that are outside of the ring, but not the benzene ring itself, right? So really harsh conditions needed to actually reduce the benzene ring. Gentler conditions will reduce double bonds outside the ring, but not the ring itself. Okay, the other special type, so this full reduction using harsh conditions is the first type of reduction reaction we're going to talk about. The second type of reduction reaction we're going to talk about is what's called a Birch reduction. Okay, notice what happens here. I go from having this nice, neat aromatic compound to, is this guy on the, what is that, on the right, is that anti-aromatic, aromatic, or non-aromatic? This is non-aromatic because we have, whoops, let's not use that color. Because we have these two sp3 hybridized carbons breaking up that, that conjugated network. We're going to see, so it uses sodium metal, right? So just pure sodium metal in methanol and ammonia. This is going to be very similar to these types of reactions we saw for reducing alkynes. We said sodium in NH3 when it's really cold will selectively reduce an alkyne to a trans alkene. The mechanism here is going to be really similar. Okay, what happens is that sodium, remember, number one thing to remember about sodium metal is it wants to get rid of that electron as quickly as possible, right? So sodium will donate its electron, and it's only got one of them. So it's like a radical reaction, initiating a radical reaction. It places an electron on that ring. So what the ring does is rearrange itself to first pair up that electron, but then also you inevitably create a radical, right? So what happens is when sodium adds that electron is you have this lone pair that's created, and on the opposite side of the ring, you have a radical electron. Why is it on the opposite side of the ring? This is really important for the type of product that we get, because those are now pairs of, or I guess they're not pairs, they're now electrons sitting in clouds, a lot of concentrated negative charge. They want to be as far apart from one another as possible. So the radical and the pair of electrons are going to arrange themselves on opposite side of the rings. Well, now this guy is a great nucleophile, right? That pair of electrons, that carbanion, great nucleophile, or base rather in this case, because it's going to reach over and grab a proton from methanol. And now I'm just left with this radical, again on the opposite side of the ring of my newly created sp3 hybridized carbon. So the next step is sort of just another round where sodium is again going to, a new sodium atom is going to donate another electron, and that's going to create another carbanion, which is going to act as a good base, grabbing a proton from methanol. And that's how I'm left with two sp3 hybridized carbons on opposite sides of the ring. Okay. Yeah. So again, these are a set of reactants, the sodium metal, methanol, and then the solvent is ammonia. There's some selectivity in these reactions if you have a substituent on there, okay? And so different substituents are going to act different ways. If you have an electron donating substituent, so what do I mean by that? An alkyl group, so for example, a methyl group, an alcohol group, an ether, or an amine group. These are all considered electron donating groups. And so you're going to get a selectivity in your reaction where the electron donating group remains bound to that sp2 hybridized carbon. So this product right here, where the electron donating group is on the newly formed sp3 hybridized carbon, that doesn't occur. Okay, so you're going to get a specificity in this reaction. It's because that electron donating group would destabilize any lone pair that was placed on it, right? So the bottom line is that if this product was observed, it would have to go through an intermediate that looks like that. But since this is electron donating, this is not a favorable intermediate. Okay, so you're going to have some selectivity when you have an electron donating group. And you're going to see the exact opposite when you have an electron withdrawing group. So what's an electron withdrawing group? Any carbonyl containing group, any carbonyl carbon would be an electron withdrawing group. So in this particular case, we have this aldehyde, that's an electron withdrawing group. A cyano group or a nitro group would also be considered electron withdrawing. And so this now is when you have your substituent group, in this case again, oh, I guess it's a ketone, not an aldehyde, sorry. This ketone group is on the newly formed sp3 hybridized carbon because it goes through an intermediate where there's a pair of electrons on that carbon and that anion is stabilized by that electron withdrawing group. So exactly the opposite of what we saw. What would not be observed is something where that group remains on an sp2 hybridized carbon. Okay, so depending on what substituent you have on your benzene ring, you expect to see specificity in these types of reactions.